So let's create a project using full adders. We'll create a 4-bit triple carry adder. So I'll do this very quickly since we are already habituated. So RCA with full adder FA, full carry adder with full adder, file RCA with adder. Next, select port. As you can see, these are the ports that are available by Xilinx by default. I will tell you how to add different boards also. Okay. If you like to close, close that project. In project summary, it is showing Arctic 7. I haven't selected Z-board, so I can change that here itself in settings, edit. I can change the board, whatever board I want. Select here, select Z-board. Okay, then okay. Committing the changes. Now it is Z-board. Now we'll start writing the code of triple carry adder. I'll write little fast. So we just, for doing a triple carry adder, we need a full adder also. First I will define a full adder module. We'll add, the full adder has two outputs, sum comma cout comma a comma b comma cin are the three inputs, and input a comma b comma cin colon output sum comma cout colon the module. Now I need to write the bit of full adder. It will require one sum output and two carryouts, internal carryouts. So let's write XOR of the sum is equals to a comma b, and will require a AND gate of, will get carry 1 a comma b, right? Then we'll require one more XOR to get, so this sum is the partial sum, right? So it will be S1. The final sum will come from sum of S1 comma Cin, then have AND gate of this S1 comma Cin, right? Then we'll have, what do we have? The output of AND gate will be my carry 2, and then we'll have a, either you can use XOR or OR gate, whatever you want, because I have already proved the OR gate and XOR gate of adding two half address will be same. So I'm using XOR. The output will be cout, and it is XOR between these two carries C1 comma. Now this is my full adder. Need to call this full adder in my ripple carry adder. So what are the port configuration of my ripple carry adder? My output should be there, and my cout should be there, and my three inputs be there. Since it is a 4-bit full ripple carry adder, I need to define it as a 4-bit inputs, 3 down to 0. My a comma b comma, only a and b are 4 bits, and my cin is single bit. And only my output will be again 3 down to 0. Sum, and other output is also single bit cout. See, I am using ABC in same here, but as I already told, inside the module the names are local, so you can use the same names. Out, done, right? No more errors. Now call that full adder 4 times. Do we require any wires? Yes, we'll require some internal wires to carry propagate. You have to propagate the carry 3 times because it is a 4-bit full adder. The first stage carry will be propagated to second stage carry to third stage to fourth stage. So these are internal carries. I'll write ICs, IC, IC, IC. Then we will call the full adder. I'll call my full adder. Don't forget, you have to give the instance name FA1, FA2 like this. So what is the, if you give same instance name, it will give error because it is telling FA1 is already declared. So you should definitely give the unique names. It can be anything. The order doesn't matter. You can write FA22, 25. It doesn't matter, but it should be unique name. So the full adder 1 should have, the first stage of full adder should have inputs A, B, C in. The A is A0, B0, and C in, and the output is sum 0 and first stage carry out IC1. Right? Same thing will copy this. Sum will be directly mapped to A1 and B1, but the carry in here will be equal to my IC1 and carry out will be IC2. Okay. My sum 2 will be mapped from inputs 2, and this carry is coming from IC2, C2, and this carry will be IC3. This should be IC3 and B3, A3. This will be sum 3, and this is my final carry, which is C out. Now your full adder circuit is done. Save it and see the design. now now you can see whether it is really calling it or not. See, it is really calling. RCA is calling my 4 full adders, FA1, FA2, FA3, FA4. The same thing should reflect there in the schematic also. So once that will appear, we will start writing the simulation. See, 4 full adders and they are connected as I described. In each full adder, you can see what is the circuit inside each full adder. This is the circuit inside each full adder. Each full adder has 2 AND gates and 3 XOR gates. This is one half adder and this is other half adder. I am adding 2 half adders with one more XOR gate. So once the circuit is ready, start writing the stimuli file. Add source, simulation source, which is a test bench. Create, I want to write top underscore RCA and finish. Don't have any input outputs. Yes. Open the top, writing the top. So first thing, we have to define what all the wires that we require. We'll require a 3 down to 0 wire of sum and wire of C out. So I will give different names so that you will get practice with all the different things. Till now I'm giving the same names, but here I'm giving different names like top underscore sum, top underscore C out. Will require registers, 3 down to 0 registers of top underscore A, comma top underscore B, right? Then we'll require a register of top underscore C in. Now you need to call your full adder with the same name. The name is RCA underscore with FA. Give my RCA and follow the order. The order is this. equals C. So in that order, I need to attach my top signal. So I am attaching like this. This is called connect by name. If you remember, we have already discussed this. Will be mapped to top sum dot cout. Will be mapped to top cout dot a will be mapped to top underscore a dot b will be mapped to top underscore b dot cin is mapped to top underscore c, right? Why still some error? Yeah, we haven't closed with semicolon. No error, right? Now start applying the signals. Start applying inputs. Now let's apply different combinations of inputs like this. We have to begin initial begin. I want to monitor here instead of display. We'll monitor the signals at every time wherever these signals are changing. What are the signals? What is my A? Percentage B, comma B, percentage B, comma C in equals to percentage B. What will be my output? I want to see the output. C out equals to percentage B, comma sum equals to percentage B slash n. So I need to map the names. The names are top A, top B, comma top C in, comma top sum. No, first I have given C out. So top C out, top sum. Close it and then start giving the input values. And this will give input in different initial block, or you can give in the same initial block also, it doesn't matter. But I want to show you all the different things that you can do in Verilog. So you can have as many initials and as many always blocks. I will discuss what is always block in next module. So I have given initial, begin, and you need to end this begin. Inside this, we'll write different combinations of A, B, C. Let's say A is equals to, I'll write in decimal, will be easy and fast. My A is top underscore A, right? So I need to write top underscore A is equal to 4, top underscore B is equal to 7, and top underscore C in is equals to 0. This should be binary, right? Because we have defined only single bit. If you define multiple bit, then you can give decimal values of like this. So this should be binary, and these are different decimal values. I will give the 4 combinations: 2, 5, 8, 3, 6. Let's say there is a carry for these two. Done. Now let's see the output of this thing. We have to give some delays, otherwise everything will execute at the same time. I'm giving a delay of 5 nanoseconds for each operation. And done. Now run the simulation. And it's done. We'll see the outputs in message window. Initially at time is equal to 0, they're all don't care, but because we haven't defined at t is equal to 0 what will be the combination of A, B and C. But at time is equal to 5 nanoseconds, A is equals to 4, B is equal to 7 and C is equal to 0. So the output is 4 plus 7 is how much it is? 11. So it is 11. It is very confusing, right? I will define them in decimal. Since I have defined in binary, they are appearing in binary. I can define them in decimal simply by changing this into decimal dot d, and this should be binary. This should be binary. This should be decimal. Run and relaunch the simulation. So this window is called TCL console window. Whatever you are doing here in the GUI, you can do the same things in using tickle script. This is called TCL. We'll call it tickle script. So what I did till now, just now, I did a relaunch simulation. So you can write directly a command relaunch underscore sim. It will do the relaunch simulation. Let me show. I copied this command and I can write here relaunch simulation. I will write the command here and then enter. If I press enter, it is relaunching the simulation and it will relaunch the simulation again. The same thing you can do different things, like first I have defined source of top, right? I have set property, all these things that can be runnable by using this tickle window, right? I have relaunched the simulation. So whatever the command you want to write, you just type it here and do that. See, it has relaunched the simulation again. Let me change one of the input and relaunch the simulation. Let's take this. Here the B is 7, but now I change the B is equal to 9. I am saving this and then I will again relaunch the simulation, and now see, automatically it is doing the relaunch simulation. I haven't pressed this relaunch simulation button, or I haven't went here and do the relaunch simulation. Why it is required to script this? We already have the GUI function, right? But why it is required script? Because scripting is very essential when you do automation. Let's say you want to do lot of optimization or lot of simulations to run. You just write the tickle script and paste all the commands here, whatever the commands you want to write, like giving the XTC file or giving the constraints, everything that you can do in the GA, you can write here, and then you run the script once, and then you can do your own work. The script will taken care of all the steps that you do. So that is the power of automation. We'll discuss one day about this thing, but right now we'll see whether the output of this ripple carry adder is correct or not. See, if you are adding 4 plus 7, the output is 11, 2 plus 3, output is 5, 5 plus 5 with carry of 1, the output is 11. Similarly, 8 plus 6 with carry of 1, the output is 15. So our ripple carry adder is working perfectly fine. So what I want to do in this module is I want to dump the same code in different boards, right? As I already told, we have only few boards that are available, like RTX board, Kintex board. I want to add few new boards also. So let's see how to add the new boards. We go to search engine and type Vivado board files. This will get a GitHub link. This GitHub Resilient Vivado boards. Open this and download this zip file. Once the zip file is ready, open the file. You will have the Vivado board masters. You can see the new board master. These are the different boards that are available by Xilinx Vivado. There are a lot of boards like RTX board, Genesis board, Nexus board, different boards. So you just copy all these boards and then paste it inside your Xilinx Vivado folder. Go to Xilinx Vivado 2019, whatever version you have installed, and go to the folder called data. Inside the data, go to boards and board files. See, these are the board files that are available by default, right? These are the boards. Whatever boards that are available in that folder will appear here. Now I am copying the new boards, so the new boards should appear here. I'm copying all the new boards here. See, all these boards, there are now 28 boards I have copied. So all these boards should appear here. If I try to select the boards again, settings, let's see, is fetching. I think it needs to restart the Vivado once. Once you restart the Vivado, it will show all the different boards that are available. Before restarting the Vivado, I want to do the simulation of this. I did the simulation. Okay, we will do synthesis and implementation once we restart the Vivado, and we will try to implement the same design, same ripple carry adder design in different boards, and we'll see the amount of utilization, resource utilization and power consumption in different boards. So I restarted the Vivado. Once you restart the Vivado, it will look like this. I'm not creating any project. I'm opening the project. All the recent projects you can see here. So I'm directly clicking the RCA project that we have defined just now. So in the RCA project, we'll try to do, see, we are still using the jet board. You can check whether the boards are added or not by clicking the edit button. Here you go to general. In general, you can select project device, which kind of device you want to use. Now see, earlier we have only 78 boards, but now there are different boards like RTX, RT, CMODs, Genesis, Nexus. All these boards are added. Spartan 7. These are earlier boards and these are the new boards, right? So in the jet board itself, we'll do first synthesis and implementation. Later we'll do the same implementation in different boards. Click OK. I haven't changed the board. Still it is jet board. So let's open our sources once. Let's see our schematic once. So in this step, I will run the synthesis and implementation without adding the constraint file. As I already told, for implementing the design on jet board or any kind of FPGA board, you will require a constraint file, right? What does that constraint file will do? The constraint file will map the designed input output ports to your FPGA board, because the FPGA board won't have these names, right? Some carry out A, B, C. They have their own input output ports. In order to map those, you have to write the constraints in the constraint file that yes, this A input should map to my switch 1, B input should map to my switch 2, and some output should map to my LED 1, some carry output should map to my LED 2, like this. So for that, you will require a constraint file. But in this example, I am not implementing on any FPGA board, so I am not writing the constraint file. I will ask the tool itself to decide the pins that it wants. If you don't add the constraint file, still the synthesis and implementation will work, but you don't have a control over the input and output pins. You cannot tell yes, this input pin should map to this input name A. If you add that in constraint file, then it will definitely map to them. But if you don't add that in, if you don't add the constraint file, the tool itself will randomly assign some input pins to these inputs and output pins to these outputs. We'll see. I am running the synthesis first without adding any constraint. I am running the synthesis. Click OK. The synthesis is done. Doing in background, running the synthesis design. Once the synthesis is done, we'll do the implementation also. You can see the steps of synthesis that are happening here. So this is the synthesis that is running. Now the synthesis is done. It is asking whether should I run the implementation or you want to open the synthesize design. So let's open the synthesize design first. So this is the synthesized design. This is the jet board, and it was synthesized on this jet board, right? But we haven't assigned any pin names and all. So for that we need to do implementation. So I'm doing run implementation. See, this is the command to run the implementation. Launch underscore runs one underscore one minus jobs. Since I selected 8 jobs, so it is like this. So next time onwards, if you want to run the implementation, just by typing the command, copy this command and paste it in tickle and then enter, then it will do the implementation. Now it is doing the implementation. We can see in messages if there are any errors or warnings that are existing in our design, or in log file you can see what is happening with the Vivado tool, what all the steps that we have finished so far. It will show everything here. And in reports you can see the reports of the synthesized design. You can see the utilization. This is the report utilization. You can see how many LUTs that are used, how many IOs that are used, everything. I will explain this. Maybe in advanced topics, we'll explain the architecture of one of the FPGA board like JET board. How does the JET board is made? What are the basic building blocks inside the JET board? We'll explain these things in the advanced topics. As of now, just see the implementation. We have already implemented. So let's open the implemented design. We want to close. Yes, close the synthesized design and implement the design. Now see, this is the implemented design. I'm zooming in. So this is my design actually. It is using these CLBs. We'll call this as a CLB. We'll explain this in advanced topic. What is a CLB? Each CLB will have two slices. This is slice 1, slice 2, and each slice will have carry chain, muxes, lookup tables. All these things we'll explain in advanced topic. But as of now, think that your design is implemented on this JET board at this particular location. Okay? And after implementing, it is assigning the pads to your design, right? See, this is an output pad that is assigned to my output called out, right? Similarly, this is one more output pad, right? It has assigned all the outputs and inputs. These are input pads, right? C out, sum, carry out, A, B, all these things are getting assigned here. Okay, this is the implemented design. Let's see the report. In the report, we can see how much power it is consuming. How much power it is consuming? It is consuming total on chip power of 3.07 watts. Okay, in this, what is the logic power it is taking? 0.26 watt. This is the actual power you need to report whenever you are reporting your design power. The IO power means the amount of power the IO is taking, but that is not your design power. It is just the power that is consumed to send the signals from external world to inside the JET board. So that is not consumed by your design. So you can ignore the IO power. You have to report your logic power. Your logic power is only 1% of your total power consumption. Okay, this is for JET board. Let's say the same design, if I implement on different board, what will be my power budget and what will be my, let's see the utilization also, how much utilization it is happening. Let's see resource utilization. Go to here, report utilization. Result name is utilization 1. So it is taking 4 LUTs, 1 slice. So this is my report utilization for this particular board. Okay, so I am changing the board. Now to change the board, go here, right corner, go to settings, and then change the board to, let's say I want to use different kind of board. Let's say a board called basis 3 board. This is one of the basic board, but it is very good board. We'll see the performance of your Ripple Caddy adder on this board. So I am changing, yes, I am naming it as synthesis underscore basis 3. Project summary, you can see the board is changed to basis 3 and it is a family of RTX 7. So now I will again rerun the synthesis and implementation. I can directly go to implementation because the implementation itself will do the synthesis. So I am running implementation. It will ask whether should I do the synthesis first. Yes, do the synthesis first and then do this implementation also. So it's running. See, it started with synthesis and it will do this implementation also. We'll see in a while. So now it is doing implementation. So synthesis is done. Now it is doing implementation. Okay, let me show some more things here. You can press this to see the actual signal flow of your this button. If you press, you can see the signal flow of your design. This is your design, right? So this is how the design is connected to your CLBs. There are a lot of multiple wires involved, right? That is why I always tell the real world outputs and ideal simulation outputs will vary a lot. In ideal simulation, it won't consider the wire delays, wire capacitance, or wire resistance. But in real world, see, it is connected from all the way from here to here. You think that it is very small line, but if you zoom in and if you actually see the length of wire, it will be in meters actually, because it is a nanometer technology. The length of wires in even in kilometers exists. So that much length of wire will have a lot of resistance, capacitance, as well as some extra parasitics, which will add delay to your signals. So the real world outputs will always deviate from the simulation outputs. That's why you have to report the synthesized or implemented output as your actual output, not the simulated output, because the implemented output will give you the true outputs compared to the simulated outputs. Okay, our implementation is done. We want to see the reports, not the implemented design. Okay, let's see the implemented design also. How does that look? See, this is the implementation on basis 3 board. Now you see the implementation is done on different location and different IOs are used, right? So this is the advantage of having RTL. You can write RTL once and you can dump the same RTL. I haven't modified my .v file of source or stimuli was not required for implementation, but I haven't modified my design source, right? But still I am able to run the same design source on different boards as well. Why? Because the RTL is independent of boards. So I want to see the utilization and power. So I'm reporting it, calling it with utilization underscore basis. So this is the amount of utilization it is having, and let's say power, much power it is having. Yeah, now see the amount of power is reduced, right? Earlier it was 3 point something. In this board, the power is 2.94 because the IOS is consuming less power and even the logic implemented in this board is less. That is because the board manufactured using different technology node and different architecture compared to the earlier Z board. So this is what I want to show you. The same design, if you implement on different boards, will have different utilizations, different amount of power it will consume, different amount of LUTs it will consume. Since it is a very small design, the amount of LUTs are same here. But if you go for very complex designs, then you will see how much utilization it is having and how much power it is consuming on different boards. With this, I will conclude this session. In the next session, we will see. Okay, one more example I want to show, the example of gate delay, right? So we'll do that as well. That will clear your delays, whatever I'm explaining, right? In the ideal world, the delays will be different compared to the simulation world. So I want to emulate the ideal world delays by adding the gate delays in Verilog code. I want to emulate. Emulate means I want to uh, give that behavior to the gates. Ideally, the logic gates here, the XOR gate, AND gate will have zero delays. But as I explained, if you add like this, it will add some delay to this AND gate, to this particular AND gate. So this will be helpful to emulate the behavior of the real world. So let's take an example for that. Let's take a small example that I already explained in theory. So let's create a project for that. Create a project, new, and call the project as gate delays. Let's take this project, RTL project, create a file, cd, I'll call. You can name anything. .v file should not be equal to your project name also. That's why I gave different project name and different .v file. Next, next. Let me select the board, our favorite board, jet board. See, I forget to explain the different things that are configured by these boards, right? See, what are all these things? You can see what are the different IOs that are available for different boards. See, different boards have different IOs, and different boards will have different power supplies. What are the LUT capacity? What are the flip-flop capacity? What is the block RAM capacity, DSP capacity? All these things. Based on this, you will select your own board, right? Based on your requirement, if you require very high IO pin count, you select this board. If you require very low IO pin count, you select different board, like this. If you require more LUTs, you select more LUTs board. And if you require different power supplies, you select accordingly. You can select your own boards. Okay. As of now, I am selecting the jet board. So jet board, next, and finish. Would you like to close the project? Yes. I made some changes. I don't, because I added some delay, right? I don't want to save it. So let's do an example on gate delay. Okay. I don't have any. I'll define there. So it created GD. So let's write very simple program. There is an output and there are three inputs A, B, C, and output Y, input A, comma B, comma C. Then let me declare some internal node I. What function I want as an output. In the example, I have shown NAND followed by OR, right? I will do the same thing. NAND, first of all, NAND gate with this internal node as A comma B, that is followed by an OR gate with output node Y comma I comma C. So what I want to give is, if you don't give any delay, it will take it as a 0 delay, but I want to give some delay. So I'm adding a delay of 5 nanoseconds as well as a delay of 4 nanoseconds. You remember, if I give only one delay, what does this mean? The 5 will be my rise delay, fall delay, as well as turn off delay, and 5 is the typical value because I'm not assigning any min and maxes. So 5 is my rise delay, fall delay, and turn off delay, as well as it is the typical value of all these three things. Similarly, the 4 is for rise fall delay of the OR gate, and 5 is for NAND gate. So my design is ready. I'm saving the design. Then I need to run a stimuli. Let's see the elaborated design. We'll follow the same steps until we get habituated. So the elaborated design. So this is my output Y. It is coming from NAND AND plus OR. The inverter is here, NAND, and then it is going to an OR gate. But there is no information about delay here, but we have given the delay. It will take the delay into consideration. We will see that by adding a test bench. So add source, add a test bench, which is a simulation source, create file, test bench. I can write any name. So here I am writing test bench, then finish, I don't have IO ports. Yes. Open the test bench. Write the code. First thing is we need to define registers and wires. Since the inputs are A, comma B, comma C, and output is Y, which is a wire of wire. Now I need to call my GD. GD is my gate delay block with some name, my GD, and in the same order I am calling them A, comma B, comma C. Okay. My block is called. Now I will give inputs in initial block, initial, begin. Now I want my A to be 1, B to be 0, and C to be 0. Initially I will give all the three things as zeros. We'll see what happens after you change the inputs. A to 1, comma B to 1, and C to 1. C is equals to 1. Then after 10 nanoseconds, this is initial, and after 10 nanoseconds I am giving this, and again after 10 nanoseconds I'll apply different pattern of ABC. A is equals to 1, B is equals to 0, C is equals to 0. Right? There is some error. Okay, C minus C equals to 0. Okay, save it. Okay, we haven't ended the initial block, so end initial block. Now no errors. Save the simulation. See, every time it is going up to 10 microseconds, right? Because the time period is this. You can tell how much time period you can run, or you can even finish the thing wherever you want. You can directly write, I want to finish my code in, let's say, 20 nanoseconds. Directly write after 20 nanoseconds, just finish my code, or after 50 nanoseconds, just finish my code. Don't run up to 10 microseconds because we don't require, right? So saving it and relaunch the simulation. Okay, cancel. There is an error. What is the error? We haven't given the semicolon. Right? Now save it and run the simulation. Now see, it didn't went up to 100 microsecond, 10 microsecond. It went up to only 70 nanoseconds. Why 70 nanoseconds? Because 10 for this, 10 for this, and 50 for this. Total 70 nanoseconds. So let's see what is happening. What do you expect the output? The output is 0 initially, and at that stage y is don't care, and the output will go to 1 after 9 nanoseconds, right? After 10 nanoseconds will go to 1. All the inputs are changing like this. Since we have given a delay of, how much we have given delay? Delay of 4 nanoseconds for 4 nanoseconds for OR gate, right? So the output will appear after 4 nanoseconds. Even though the input is changing here, the output for this, let's say, what is the functionality of y? Y is equals to a dot b whole bar plus c. At this particular node, a dot b whole bar, what is a dot b? It is 0, whole bar is 1. 1 plus 0 will be 1, right? But it is not 1 because we have added some delay. That delay should be considered. After that amount of delay, it will go to 1, right? That is why the output is shifted version of output. This thing is tricky, but it is very, very essential to understand this thing. The output is 5 nanoseconds shifted because we have added a 5 nanosecond delay of NAND gate. The output is 5 nanosecond delayed and appearing here after 29 nanoseconds. Ideally, it should appear here, but it is appearing here, right?